welcome to Unit 5. Very exciting stuff. Alright, let's talk about some exponentials and some absolute value. Basically, this unit is all about functions and systems of equations. So we're going to start with exponential because that's something you've done before, and we'll expand upon it a little bit. So, your standard equation of an exponential function looks like this. Where A is your initial value, and B is what we're going to call our growth or decay factor. And so the big idea with exponential, like talking about the rate of change of an exponential function, we have linear equations which have a constant rate of change, meaning you're adding or subtracting the same amount each time. Exponentials have a multiplicative rate of change, meaning we're multiplying by the same thing every time. And that thing we're multiplying by each time is what we call the common ratio. So, for some examples for you, let's say I have f of x equals 2 to the x. Also, just a reminder, f of x, that's just function notation, same thing as saying y. And if I was to make myself a little table, let's see. All right. So I could just plug in my values here. First thing I see, another way I could write this would be like 1 times 2 to the x, which tells me my initial value is 1 and my b is 2. And so we just need to see, like, how can we tell if this is growth or decay? Well, if I take a look and just start plugging in numbers, I'm going to start with 2 to the 0 because I know that anything to the 0 power is 1. And now if I plug in 1, 2 to the first power is 2. If I plug in 2, 2 squared is 4. If I plug in 3, 2 cubed is 8. You see how I am multiplying by 2 every time as I go down the table? Well, that means if I were to go back up the table, I'm dividing by 2 every time. So I'd get a 1/2 and a 1/4, which comes in with negative exponents. If we remember, 2 to the negative 2 is like 1 over 2 squared, which becomes 1/4. And so this one, I see as I go down, we have growth. Let's look at another example. Let's say I have a different function, g of x equals 1/2 all raised to the x power. Okay. I'm going to start with 0 again because anything to the 0 power I know is 1. And that follows because another way that we could write this would be like 1 times 1/2 to the x. So my initial value is 1. My growth/decay factor is 1/2. And so 1 to the 1/2 power is 1/2. 1/2 squared gives me 1/4. And 1/2 cubed gives me 1/8. So you see how as I go down the table, I'm dividing by 2, which means as I go up, I can times by 2. And so this one is decay. So how do I know if I have growth or decay? It's all about the b value, or whatever your exponent is attached to. If it's bigger than 1, then it's growing. If it's less than 1, it's decaying. If it's 1, then that's just multiplying the initial value by 1 every time. And so that would actually not be changing at all. So, example. We're going to determine the initial value and the growth or decay factor. Okay, so for example, A, my initial value is going to be 60 because that's what's out front of what's attached to the exponent. And I can see this is growth because it's bigger than 1. So my growth factor is 1.41. Another example here, I'm going to abbreviate initial value with IV. It's 23. And this time, I'm going to have a decay factor because it's less than 1. And my decay factor is 0.67. Cool. Well, we also need to talk about the growth decay rate. Okay, the growth decay rate is the percentage change between, or I should say percent change, is the percent change between each output of the function. So, meaning, if I was to look back at our example of the table, let's look at our first example. You see how from 1 to 2, it doubled. From 2 to 4, it doubled. From 4 to 8, it doubled. That is a 100% growth every time if it doubles. Or here, from 1 to 1/2, it cut in half, cut in half, cut in half, which was a 50% decay. And so, how do you think I got that? All right, so we find the growth decay rate by how far the factor is from 1. So, for example, my first example, my initial value is going to be 5. I know this is growth because it's bigger than 1, and my growth factor is 1.47. My growth rate is how far is that factor away from 1. So that would be 0.47, which is a 47% growth rate. Okay, I could also have something like y equals 4 times 0.78 to the x, or my initial value is the 4. This time it's decay because it's less than 1, so my decay factor is 0.78. Well, my decay rate, how far is that away from 1? Well, I can just do 1 minus that. And we get 0.22, which means the decay rate is 22%. Okay. And last thing with this, well, 2 more things. I'm going to do the same example, kind of example. This one's a little bit different because now I have this 4x in here. My initial value is still 100. We're going to pull out properties of exponents for a second because this is the same as 100 times 1.05 to the 4th all raised to the x. So that's like multiplying your exponents. And so in my calculator, I can do 1.05 to the 4th and 1.22 to the x. So that means really my growth factor is 1.22, which makes my growth rate 22%. Let's do another example like that. Something like this. Once again, I could pull up properties of exponents because this would be equivalent to 0.68 to the 3rd all to the x, which means this is really 70 times, let's see, 0.68 to the 3rd becomes 0.31 to the x. So my initial value is 70. This time my decay factor is 0.31 and my decay rate is 69%. Okay. If you have questions there, let me know through email or something. Just want to do word problems real quick. Okay, in this question, we're just piecing together what we know. So like between initial value, growth rate, growth factor, all that jazz. So my initial value, what we started with, is $100. We know that the growth rate is 4%, which as a decimal is 0.04. Well, that means my growth factor is 1 plus that amount, so 1.04. So my equation that I could put together is 100 times 1.04 to the x. And x in this case is time, and so if we want to know how much is left in there after 12 years, we go 1.04 all to the 12th, and now we're going to type that in our calculator. 100 times 1.04 to the 12th. $160.10. Let's do one more. Okay. Tennis tournament. We initially have 128 participants. It's cutting down, so we have a decay, and my decay rate is cutting in half every time. So cutting in half is 50% to 0.5. So that means the decay factor is always 1 minus the decay rate. So in this case, 1 minus 0.5 is still 0.5. So it means my equation is 128 times 0.5 to the x. We want to know how many are left after 5 rounds. So 128 times 0.5 to the 5th. So after 5 rounds, they get down to 4 players.